Let's see what happens when you multiply two powers together. But first, what's 2 to the third power? Exactly, 2 to the third is 2 times 2 times 2, or 8. Let's hold on to this down here. And what's 2 to the fourth power? Nicely done. 2 to the fourth is 2 times 2 times 2 times 2, or 16. Next, let's multiply these powers. So we'll take 2 to the third and multiply it by 2 to the fourth. So what does this equal? Well, 2 to the third is 2 times 2 times 2, and 2 to the fourth is 2 times 2 times 2 times 2. So all together here, we have 2 times 2 times 2 times 2 times 2 times 2 times 2. Yikes! Instead, let's write this as 2 to some power. So what is the missing exponent up here? Right, in total, we're multiplying 7 2's here, so this equals 2 to the 7th power. So we multiplied 3 2's by another 4 2's, giving us a total of 3 plus 4 2's. 3 plus 4 is 7, so it makes sense that 2 to the third times 2 to the fourth equals 2 to the 7th. So for expressions like this, you can just add the two exponents to find the exponent in the product. Let's make sure that's right. 2 to the third is 8, and if we multiply that by 16, which is 2 to the fourth, we get 128, which is 2 to the 7th. So this equation checks out. Next, let's try another example. Say you have 7 to the 8th power, and you're multiplying it by 7 to the 5th power. So you're multiplying 8 7's by another 5 7's. This product equals 7 to what power? Right, you can add these exponents. In general, whenever you multiply powers with the same base, so for this example, the base was 7, the number that you're multiplying over and over again. So when you're multiplying powers with the same base, you can add the exponents. In this case, 8 plus 5 is 13, so this product is 7 to the 13th power. Let's look at one more example. In which of these expressions do the powers being multiplied have the same base? So which of these expressions can we simplify using this rule? Right, down here, both of these powers have a base of 5. So if you multiply them together, you get 5 to what power? Exactly, the exponent here is 5 plus 3, which is 8. Okay, here's one last challenge for you. Suppose you have 7 to the second power, and you're multiplying that by 7 to another power, and this product is 7 to the 6th power. Can you figure out what this missing exponent has to be? Precisely. Adding 2 to this missing exponent had better give you 6, so this exponent has to be 4. Nicely done. Let's see what happens when we divide powers. But first, let's make sure you're comfortable multiplying them. If you have 4 to the 5th power and then multiply it by 4 to the 3rd power, you'll get 4 to another power. What's the value of this exponent over here? Right, you can add these exponents. So 3 plus 5 is 8. So 4 to the 3rd times 4 to the 5th equals 4 to the 8th. Now let's try dividing 4 to the 5th by 4 to the 3rd. Well, 4 to the 5th equals 4 times 4 times 4 times 4 times 4, a total of 5 4's. And we're dividing by 4 to the 3rd, which is 4 times 4 times 4. You can cancel out a whole bunch of these 4's. To simplify this fraction, why don't you select which 4's you would cancel out? Exactly, so there's lots of cancellation. The 3 4's in the denominator here will cancel with 3 4's in the numerator. You could have picked any 3 4's in the numerator, like these 3. So after canceling out all these 4's, 4 to the 5th divided by 4 to the 3rd equals 4 times 4, which is 4 raised to what power? Great, so 4 to the 5th divided by 4 to the 3rd equals 4 squared. You can think of this as starting with 5 4's being multiplied together, and then you're canceling out 3 of them. And that leaves 5 minus 3 4's that you're still multiplying together. So this exponent in the answer is 5 minus 3, or 2. Let's double check our answer to make sure it's right. 4 to the 5th is 1024, and 4 to the 3rd is 64. If you check on your calculator, 1024 divided by 64 is 16, which is indeed 4 squared. In general, whenever you divide powers with the same base, so these two powers have the same base of 4, then you can subtract their exponents. Try another example. Say you're dividing 3 to the 17th power by 3 to the 11th power. This equals 3 raised to what power? Precisely, 17 minus 11 is 6, so this quotient equals 3 to the 6th power. Okay, for your final challenge, here are 2 more equations, and each has a missing exponent. See if you can figure out what those exponents are. And remember that whenever you see a number without an exponent, like this 6 over here, that's the same thing as saying 6 to the 1st power. Okay, now find those exponents. Excellent! So you can think of this 6 over here as being 6 to the 1st power. That means this exponent down here is 4, because 5 minus 4 equals 1. And over here, you were looking for a number that you could subtract 3 from and leave you with 8. And that number is 11. So again, nicely done. Just as multiplying powers with the same base means you add their exponents, dividing powers means you subtract their exponents. Let's see what happens when we take powers and raise them to other powers. But first, can you evaluate 4 to the 3rd power? Right, 4 to the 3rd power is 4 times 4 times 4, which equals 64. Now what happens if we take 4 to the 3rd power and then raise it all to the 2nd power? Well, squaring 4 to the 3rd means we're multiplying 4 to the 3rd by another 4 to the 3rd. And this product is 4 raised to some power. What's the missing power or exponent over here? So if you're multiplying 4 to the 3rd by 4 to the 3rd, how many 4s are you multiplying all together? Right, when you multiply powers with the same base, you can add the exponents. So 4 to the 3rd times another 4 to the 3rd is 4 to the 6th power, because 3 plus 3 equals 6. Let's look at another example. Suppose you're raising 2 to the 5th power, and then you raise that to the 4th power. So that's 2 to the 5th times 2 to the 5th times 2 to the 5th times 2 to the 5th. This equals 2 raised to what power? Exactly, we're multiplying a total of 20 2's here, so this is 2 to the 20th power. So 2 to the 5th to the 4th equals 2 to the 20th. You might have noticed a pattern here. When you raise a number to one power and then to another power, that's the same as raising it to a single power that's the product of those two other powers. So up here, 3 times 2 equals 6, and over here, 5 times 4 equals 20. Try applying this rule to another expression, 7 to the 9th power, then raised to the 11th power. This equals 7 to what power? Exactly, so the missing exponent here is 9 times 11, or 99. So 7 to the 9th, then raised to the 11th, equals 7 to the 99th power, meaning you're multiplying a total of 99 7s together. Next, go ahead and identify which of these expressions here are equivalent to 5 to the 24th power. Excellent! So these were the two correct answers here, because 3 times 8 is 24, and 6 times 4 is also 24. 12 times 12 is 144, and 3 times 7 is 21, so those do not equal 5 to the 24th. Now here's a challenging question. 3 raised to the 50th power equals 9 raised to some power. Find this missing exponent, or click here if you get stuck. Brilliant! So this exponent must be 25, and that's because you can rewrite 9 as 3 to the 2nd power, and 50 equals 2 times 25. So nicely done. Next, say we're raising 3 to the 5th, and then we raise that to the 6th, and then we raise that to the 2nd. All of this equals 3 raised to what power? And click here if you'd like to review parentheses and brackets instead. Right. Here you multiplied 5 by 6, and then you multiplied again by 2 to get a total of 60. So this expression equals 3 to the 60th power. Now one more thing. Say you're raising 2 to the third power. We've always been putting parentheses around these expressions before raising to another power, like the fourth. So because of the parentheses, this means you're first raising to the third and then raising to the fourth. And this equals 2 raised to the 3 times 4, or 12. But what if we leave out the parentheses? So we have an expression like this, 2 to the third to the fourth. Well, this means something a little different. By convention, order of operations actually says to evaluate the exponent up here before looking at the exponent down here. So first, you'd evaluate 3 to the fourth power, which is 81. So this expression equals 2 to the 81st power, which turns out to be a lot larger than 2 to the 12th. Try a few more examples. Here are expressions with exponents of 5 and 2, but the order is different and there are some parentheses here as well. For each equation, what's the missing exponent?
Great! Because of the parentheses here, you're first raising 3 to the fifth and then squaring it. So that's a total of 10 3's being multiplied, and this is 3 to the 10th. You get the same answer over here, raising to the second and then to the fifth. But down here, order of operations says to evaluate the 5 squared before doing anything else. So this is 3 to the 25th. And over here, 2 to the 5th is 32. So this is 3 to the 32nd. So when you're raising a power to another power, pay careful attention to whether there are parentheses. And when there are parentheses and you're raising to the powers one at a time, it's equivalent to multiplying the exponents together.